For our first example, we want to solve and graph the solution set of the polynomial inequality x squared minus x is strictly less than 20. And that strict inequality is an important detail that we need to be mindful of. So the first thing you want to do, just to be consistent, is pull over that 20 to the left side and write this as x squared minus x minus 20 is strictly bigger than 0 instead. Then once we have this thing set up, we'll put this back in the form of an equality, so we'll use that to find our boundary points. So we'll say that this implies the equality x squared minus x minus 20 is equal to 0. And for this, again, I'm assuming we're getting more and more comfortable with these sorts of things, that we can recognize what's going to happen in terms of those values, that this is a factorable quadratic. We need factors that multiply to negative 20 and add to negative 1, which would mean that we would want a negative 5 and a positive 4, or this factors as x minus 5 times x plus 4. It's a weird 4. And then from there, again, we're going to use that zero product principle. It comes up all the time. That's why we reset like this, not just because it's more familiar, but because it gives us the all-important zero product principle, which tells us that our boundary values, I'm going to abbreviate those BVs, are at x equals negative 4 and 5, because those are the places where we can have the potential change. Those are the places where our function here would be 0, where it crosses the axis, can't do it anywhere else, so we can think always in terms of just those locations, where that means we can break down our number line into the three regions from negative infinity to negative 4, from negative 4 to 5, and from 5 to infinity. And if we want to check these, what we have to do is pick a representative from each, or we should understand that we are picking one point from each of those intervals and are sure that nothing else can happen in between except for what we would expect for being positive or negative, because there's nowhere else except at these boundary points where it could possibly change, or it could possibly flip over the axis. Only crosses there, can't skip, can't jump, these things are continuous. It's got to just go within the same types of values. And for our first set, for our first interval, which is from negative infinity to negative 4, you can pick any value you want to. I usually pick the ones that are pretty close to the most manageable end. So in this case, I'm going to take x is equal to negative 5, but understand that's entirely arbitrary. I could pick anything less than negative 4 and it would work, because everything less than negative 4 should have the same flavor in terms of being positive or negative with regards to that function value, because the only place that it can change is at negative 4 or 5. But I'll pick negative 5. And at negative 5, we have that our function is going to be in the flavor negative 5 squared minus a negative 5 minus 20, where you'd end up with 25. And here, subtract 5, you would end up, you don't subtract 5, you end up adding a 5, because you have minus a minus 5, you would get 25 plus 5, I'm not being very confident right now, is 30 minus 20 equals 10. I had that written down. It's weird that it gave me trouble, but that's what you'd end up with, where importantly, that is bigger than 0. And remember, what we're looking for here are values where this relationship is bigger than 0. And you can't possibly change to being negative along this window. So, because it's negative here, we have that f is negative, or excuse me, not negative, positive, because f is positive at that one point. F is positive throughout the entire range of that interval, since it cannot possibly change anywhere until negative 4. And then we're going to do the same thing for the middle interval in here from -4 to 5. And again, I usually tend towards taking something reasonable that's close to one of the ends. But if I ever am in a situation where I can take x equals 0 for this type of thing, I will take x equals 0 because x equals 0 is almost always the best option, the most reasonable thing that we can work with, and at the very least it's the easiest to compute around. So I'm going to pick x equals 0 because 0 is between -4 and 5. I'll take f at 0, which would be 0 squared minus 0, I'll throw it in parentheses just to be sure, minus 20, which is not super interesting or involved, and just ends up being minus 20. Like I said, it's usually very easy to compute at 0, which here is less than 0 overall. And because it is less than 0 overall, that means our function f is negative on the interval from -4 to 5, because the only places it can change are at -4 and 5, so in the middle it's always got to have the same overall behavior of being negative in there. It might get closer to being positive somewhere other than 0, but that's what we're stuck with here. And then finally, we want to check at the interval from 5 to infinity, where I know I'm really low on space here, so I'm going to be a little bit more brief with my notation. And again, there isn't really an obvious candidate, so I'm going to take x equals 6. If you don't have something obvious like 0 or 1 or -1, just pick something close. And that will give me f of 6, in this case, is going to be 6 squared, 36, minus 6, so you'd end up with 30 again, or subtracting 20, 10, which, as we saw before, is bigger than 0. So we have that f is positive on the interval from 5 to infinity. It's positive everywhere along those sets of potential values. And as a result, looking at these three intervals, we can see that our function f is positive on the first, positive on the last, and negative in the middle. That means where we're looking for here, that the function is bigger than 0 overall, will be satisfied here and there, but not in the middle. So our solution set will consist of the range there on the outsides. That is, the range from not -4 to infinity, -infinity to -4, union, along with the set from 5 to infinity, which, if we want to graph, and we usually do, we can present like so, getting our potential values there. And the big subtlety, the big difficulty here is in understanding that when you take one of these test values, you are taking a representative of the whole interval, not just a single space. It takes a bit to get used to. It's very different from a lot of what we've seen so far, so be patient working through this stuff. It's very, very notational, and I know that lots of notation tends to make things very scary for people who aren't super comfortable with math. But we'll have more examples here, and we'll do one more example now with a bit more of an applied context that'll hopefully help clarify things.